last section, we talked about unit vectors, and I did define a unit vector as any vector with a magnitude of 1 in any direction. That means that there are an infinite number of unit vectors. But fortunately, there are 3 unit vectors that are important in this course that you need to always remember. You have the unit vector in the x direction, which is represented by I. Then you have the unit vector in the y direction, which is represented by j hat, and the unit vector in the k direction, which is represented by k hat. Now, generally, if you have any vector, let's say vector A, and if that vector is located in the first quadrant as shown in this diagram, it means that we can resolve or decompose vector A into 2 components. You have the component along the x direction and the component along the y direction. Now, the unit vector along the x direction is represented by I, and the unit vector along the y direction is represented by j. That essentially implies that vector A can be rewritten as axi hat plus ayj hat. So we really have represented vector A in terms of its components in the x direction and in the y direction. So this is ay. Now, if you remember what we did in the previous lesson about SOHCAHTOA, you would see that the sine of theta is gonna be equal to opposite ay divided by the hypotenuse. The hypotenuse here is just a, which is the magnitude of a, all divided by a. That means that ay is equal to a sine theta. And similarly, cosine of theta is equal to ax divided by a. That would mean that ax is equal to a cosine theta. So this is the component along the x direction, and this is the component along the y direction, and we have simply used trigonometry to represent that. That means that vector A can be rewritten as a cosine theta I plus a sine theta j. This is another way that we can represent vector A. But the real thing, we're going to do this in detail later, but the real thing I want you to remember is this. If we use the Pythagorean theorem, you will see that the magnitude of vector A all squared is equal to ax squared plus ay squared. What that means is that A is equal to the square root of ax squared plus ay squared. This formula right here gives us the magnitude of vector A. Now, I may require you to calculate a unit vector in the direction of A. Let me say that again. To calculate a unit vector in the direction of A, now I'm going to represent that unit vector A hat. A hat represents a unit vector in the direction of A, of vector A, and A hat will be equal to vector A divided by the magnitude of vector A. Will be given by vector A divided by the magnitude of vector A. That means that A hat is just equal to axi plus ayj divided by the square root of ax squared plus ay squared. Now we're going to do some examples to illustrate this. we're going to do some examples to illustrate this. Let me do an example. Let's say we have this is the y-axis, this is the x-axis. Let's say that John moves a displacement, the displacement of John, I'm going to represent the vector D, is 10 kilometers at a certain angle, let's say 30 degrees, to the horizontal. Then you can see that the x component of John's displacement dx is just given by d cosine theta, and the y component of John's displacement dy is just given by d sine theta. So this means that dx is equal to 10 kilometers. This means that the x component of John's displacement is equal to 10 kilometers cosine of 30 degrees, and the y component of John's displacement is 10 kilometers the sine of 30 degrees. This right here will be equal to 5 kilometers, and this right here will be equal to 5√3 kilometers. Now, the next thing I would like for us to do is to look at some important properties of vectors. The very first that we will consider is scalar multiplication of vectors. Scalar multiplication of vectors. Now, a scalar is a number. A scalar is a number. That number can either be positive or negative. When we multiply a vector by a scalar, what we get is a vector with a different dimension, with a different magnitude. For example, if we have a vector A, this is our vector A. Suppose we have a scalar which is any number k. If we multiply A by k, as long as k is positive, we are going to get a new vector. This will be ka. Now, here's the deal. If k is positive, then A and ka will be in the same direction. If, on the other hand, k is less than 0, A and the vector ka will be oppositely directed. For example, that means that if A is in that direction, this is vector A, ka will be in the opposite direction. So the takeaway from this is, when you multiply a vector by a scalar, the result is still a vector. But the direction of the vector will be the same if the scalar is positive, or opposite if the scalar is negative. Now, the next property of vectors will be, let's look at equality of vectors. Equality of vectors. Two vectors are equal if and only if they have the same magnitude and the same direction. Let me say that again. When two vectors have the same magnitude or length or size and the same direction, we say that those vectors are equal. Now, even though they are equal, they may not have the same point of origin. In other words, if you have a vector A, this is a vector A, and another vector B, you recognize that A and B have the same magnitude and the same direction, so we can gladly conclude that A is equal to B. But at the same time, vector A, if I do a coordinate system, this is Y, this is X, this is vector A. Vector A can be written in that direction, and vector B can be in that direction. This is vector B. You recognize that A and B have the same direction, but they have different points of origin. So the two vectors must not start at the same point, but they must be equal in size and in direction for the two vectors to be equal. Now, if on the other hand, if you have a vector A, which is in that direction, and another vector B, which is in the opposite direction, you will recognize that vector A is equal to negative vector B. They are equal in size but oppositely directed. Now, the vector B is called the negation of vector A. It's called the negation of vector A.